Hi everybody. Uh, in continuation of last week, we want to review some basic fundamentals which you read in your bachelor course, and as they are important, I want to have a short review on them today. This is part 2. The first quantity I want to discuss about its viscosity. If you remember, viscosity is the resistance of a fluid, either liquid or gas, to a change in shape or movement of neighboring portions relative to one another. And this makes what you see as the difference between, for example, water and syrup, as shown in the figure. For the Newtonian fluids, which we are working with in this course, and most common fluids such as water, air, gasoline, oils are Newtonian ones. The relation between shear stress and rate of deformation, as you can see in the figure, is a linear one. The slope of the line, as you can see here, which is taken from the Newton law of viscosity, is shear stress divided by the rate of deformation. So the angle or a slope of the line for example, oil is larger than water and water is larger than air. So the gradient of the line here shows the viscosity. So if you want to calculate the viscosity, you can divide shear stress by the rate of deformation, or if you have the viscosity, then multiplying by the rate of deformation, you can calculate shear stress. Actually, we have two types of viscosity: the dynamic or absolute viscosity versus kinematic viscosity. Here we are discussing about both of these type of viscosity definitions. The first one is the dynamic viscosity or absolute viscosity, which is generally shown by mu, is defined as the shear force per unit area required to drag one layer of fluid with unit velocity past another layer a unit distance away. Based on the definition, the unit for the absolute viscosity will be mass over length area, for example, kilogram per meter per second, or it can be written as Newton second per square meter or Pascal second. Please note that mu or absolute viscosity is often expressed as poise, where poise or 10 poise is 1 kilogram meter per second. Another more common term is centipoise, which is 100th of poise, or poise divided by 100. For example, the viscosity of water at normal temperature is around 1 centipoise. Kinematic viscosity, as you can see here, is the ratio of dynamic viscosity to mass density, and its unit, as you can see here, has no sign of force or mass, so it is named as the kinematic viscosity. It is meter square per second. But again, like absolute viscosity, where poise or centipoise is generally used, because the viscosity of the fluids is low, and it's better to express them as centipoise or even centistoke, as you can see here. Stokes is another unit for the kinematic viscosity, where 1 stoke is 0.301 meter square per second. Here are some typical values, as you can see. For example, for water, kinematic viscosity is around 1.14 centistoke, and for air it is something like this, and for mercury you can see here. Actually, kinematic viscosity has a very important is a very important parameter, generally known as the momentum diffusivity, and we'll discuss about that later. Just know that nu is also known as a parameter which shows how the momentum is diffused into the fluid. If nu is higher, then momentum diffusivity is higher in the fluid. Viscosity is a function of temperature for liquids and a function of temperature and pressure for gases. Regarding temperature effect, as you can see here, for the liquids, increasing the temperature decreases the viscosity, while for the gases, by increasing the temperature, the viscosity will also be increased. This is an important characteristic and difference between liquids and gases. You can see here some examples. For example, for glycerin oil, engine oil, actually water, you can see that by increasing temperature the viscosity is decreased, but for gases like air and hydrogen, viscosity is slightly increasing with increasing the temperature. Please don't forget this. There are different types of examples or problems which can be solved by even this simple formula, tau equal mu du over dy. There are different types of problems which can be defined. For example, if someone give you the u function as a function of y, like this example, if the velocity distribution over a flat plate is given by this u, which is a function of y, in which u velocity in meter per second at a distance y meter above the plate, determine the shear stress at y equal 0 or 0.15. Take dynamic viscosity, you remember that this is mu, as 8.63. Whenever you face such a problem and the problem asks you to determine the shear stress, then the formula is the Newton law, and this is the simplest type of problem actually, because in this case you can take the derivative of the function which the problem gives you. For example, here you can take the derivative, multiply it by viscosity, and put y, the required value. For example, if the problem asks you to solve the problem at y equals 0, after, please note, after taking the derivative, you can substitute the value for y. Okay, let's see what happens here. This is u value. You can calculate du over dy. Then you can calculate du dy at the specified location, y equals 0, y equals 0.15. These are the values. Mu is given as poise. Please don't forget that you should convert it to Newton second per square meter or kilogram per meter second. Dividing poise by 10 gives the SI unit. Then it's just enough to substitute in the formula, and you will be given the value of shear stress at y equals 0 and y equals 0.15. What you can see here is that, as you can see, the shear stress at the surface of the plate is more than the value of shear stress at a distance of 0.15 from the plate. This is an important result. So the maximum shear stress happens at the surface, and as you go far from the surface, the shear stress will be decreased. I will discuss about this again. This is another type of example. In a fluid, the velocity measured at a distance of 75 mm from the boundary is 1.1 meter per second. The fluid has absolute viscosity mu of this and relative density of this. What is the velocity gradient and shear stress at the boundary, assuming a linear velocity distribution? Okay, this is a sketch of the problem. There's a flow over a flat plate. The velocity distribution is taken as linear, and you can see later that this is not a valid assumption everywhere, but for the sake of simplicity For this example, consider that the profile is linear, starting from 0 at the surface to the free stream velocity at the boundary layer edge. The problem says that at a distance of 75 millimeter from the surface, this is the value of the velocity. Okay, what the problem wants? The problem wants us to calculate shear stress. As you know, shear stress is the viscosity multiplied by the velocity gradient, rho u over rho y. Do we have the viscosity? Yes, the problem gives us here the viscosity, so mu is defined. Do we have rho u over rho y? Yes, we can calculate from the assumption of linear velocity profile. Please note that if the velocity is not linear, then it's not possible to calculate in this way. But here, as the velocity is taken as linear, here, assuming a linear velocity distribution, so you can simply divide 1.125 divided by 75, convert it into meters, and this is the value of rho u over rho y. Multiplying these two parameters, you will get the shear stress. Let's have another example about the shape of velocity profile in actual case. Actually, in the actual case, the velocity profile is not linear, as I told you before. There's an example here. A flows over a flat plate as shown below. The flow is laminar and the boundary layer forms on the plate. Circle the letter of the statement that best represent the velocity profile. Which one is correct for this figure? So you can see that 5 type of different flow velocity profiles are given here, and the problem asks you which one is the correct one. Okay, let's start from the first. Is this a correct one? No, this is wrong. Why? Because the actual velocity profile is not linear, and there is no sharp change from the linear to the constant velocity, as you can see here. So this is not the right answer. What about the second one? Is this the right one? No, because the actual velocity must eventually reach the free stream velocity. The free stream velocity, as you can see here, is u infinity, but here you can see that it does not reach to the free stream velocity, so this is also wrong. What about this? This is also wrong. Why? Because the velocity gradient is more near the surface, but here you can see that the velocity gradient is less near the surface. Please don't be surprised if the gradient here is much more, because the gradient, as you can see later, is not the angle between the tangent to the horizontal. It is the angle between the tangent to the vertical. Okay, finally, okay, let's pass it. What about this? This is also wrong. Why? Because the velocity at the surface here must be 0. As we name it, no slip condition. No slip condition means that the velocity at the surface is equal to the surface velocity. If the surface is stationary, then the velocity will be 0. If the surface is moving at a velocity, for example, v, then the velocity of the fluid at the surface will also be v. But here the surface is stationary. As you can see here, there's a fixed flat plate, so the velocity at the surface shall be 0. But here you can see that it is not 0, so this is also wrong. What about this? This is the correct one. Why? Because the velocity at the surface is 0, that's okay. Velocity gradient decreases by increasing distance from the surface, that's okay. And velocity reached to the free stream velocity at the edge of the boundary layer, as you can see here. So this is the right answer. Let's have another example for a parallel plate arrangement of the type shown above, or below actually. It is found that when the distance between the plates is 2 mm, a shearing stress of 150 Pascal develops at the upper plate when it is pulled at a velocity of 1 meter per second. Determine the viscosity of the fluid. So that's again an application of the same formula. Here you have tau 150, here you have du over dy. Why? Because of the small distance between the plates, please note, because of the small distance between the plates, you can assume that the velocity profile is linear. So here, as you can see, a linear velocity profile is assumed. And if the velocity distribution is linear, then du over dy can be calculated simply as u over b, where u is the velocity of the upper surface and b is the distance between the two plates. So this can also be calculated because you have u as 1 meter per second, you have b, don't forget to convert it to meter, and substituting in the equation, as you can see here, you can simply calculate viscosity. This is the basic of some of the viscosity measurement devices, like for example this one, which is a rotational viscometer. You can search in the net to know more about the different methods which are used to calculate the viscosity of liquids. Okay, when you calculate the shear stress, then it's simple to calculate force, because force is as you can see here, tau multiplied by the area where tau is applied. So knowing the area and tau or shear stress, you can then multiply them together and you will calculate F. If you substitute for the value of tau, then force is mu A du over dy. Please note that A is the contact area between the plate, for example, and the fluid. An example for this case, a flat plate with a given area is pulled at a given velocity relative to another plate located at a known distance. The fluid separating them being water with given viscosity. Find the force and power required to maintain that velocity. Okay, here you want to calculate the force. So the force, as we discussed in the previous slide, is shear stress multiplied by A. A is given here, as you can see, and tau is mu du over dy. Mu is given, I think, here, yes. And du over dy is again equal to u over the distance. Why? Because we are assuming a linear velocity distribution because of the small distance between the plates. So you can calculate tau and then multiply by area, you will get F. Multiplying F u, you will get the power required to move the plate. And this is a problem for you, students. Please solve it, and then I'll inform you how to send it to me in the Telegram channel. Okay, for the time being, please solve it, keep it with yourself, and I'll inform you how to send it to me. Another very important topic is the variation of shear stress, both in the normal to the surface direction and along the surface. Let's first have a review on the shear stress distribution normal to the surface. Suppose that we have a plate as is shown here. The free stream velocity is VE from left to right. As you can see, a boundary layer is formed on the plate. This is the boundary layer edge, this blue line. As you may remember from last session, the boundary layer is a layer where the velocity is varying in the boundary layer, and outside the boundary layer there is no velocity change. Actually, this is the effect. The effect of viscosity can be confined in this layer, which is named boundary layer. Okay, as you can see here, this is the velocity profile. We discussed about that. Velocity at the surface is 0. Velocity gradient du over dy is large near the surface, and velocity gradient will be smaller far from the surface. And finally, velocity gradient du over dy is 0 outside the boundary layer. So velocity at the surface is 0. Velocity gradient decreases by increasing distance from the surface. velocity reach the free stream velocity at the edge of boundary layer. It will not then change. Okay, so before drawing the variation of shear stress normal to the surface, please note that velocity gradient is the angle between tangent to the velocity profile and vertical axis, not horizontal axis. I would like to repeat this again and again because I'm afraid while I'm repeating it many times again, I may see that you have mistake in the final exam. Hope this is not the case. Okay, so we want to draw the variation of shear stress normal to the surface. So the velocity gradient near the surface is maximum, it will decrease as far from the surface, and finally outside the boundary layer it will remain constant. Just one moment, stop the video and try to draw the variation of shear stress normal to the surface. Then you can replay again and see the answer. Okay, okay, I hope you draw it, but if not, please check your answer with this drawing. This is the shear stress profile near the surface. As you can see, where the velocity gradient is maximum, you have the maximum shear stress at the surface, and as the velocity gradient is decreasing because of this formula, the shear stress will also be decreased up to here at the edge of the boundary layer, because at the edge of the boundary layer the velocity gradient will be 0, as you can see here. So the shear stress at the edge of the boundary layer will be also 0 and will remain the same outside the boundary layer. If not understood what I said, please replay this section because this is a very important section in our course. Okay, next come to the shear stress variation along the surface or among the surface. Suppose we have the same situation, a flat plate where free stream velocity is flowing from left to the right, a boundary layer is formed on the flat plate, and as you can see, this is the distribution of velocity along the surface. There's an important point here again, and this is also a very important slide in our course. As you can see here, for example, near the leading edge of the plate, this is the leading edge where the flow starts. Near the leading of the plate, the thickness of the boundary layer is small. So in this small distance, within this small distance, the velocity should reach from 0 to the free stream velocity. As you go further downstream, you can see that the thickness of the boundary layer, delta, will be increased. But again, the velocity should reach from 0 to the free stream velocity. Again, here. So the velocity here on the surface, at the surface, is 0. The velocity here at the edge of the boundary layer, either here, is u infinity. What happens is that the velocity profile is more stretched, okay, because the 2 points here and here endpoints are fixed. When the velocity profile is stretched, it means that the angle of the tangent to the horizontal will be increased. And again, remember, velocity gradient is the angle between tangent to the velocity profile and the vertical axis, not horizontal axis. So does it decreases or increase with x? Can you answer? By it I mean du over dy at y equals 0. What do you think? Does it decrease or increase with x? I hope you answer it correctly, and yes, the velocity gradient will decrease as you go further along the x direction. So the shear stress along the surface will be somewhat like the one you can see here. Okay, these two topics were very important, as I said. The next quantity I want just to have a short review is density. You know certainly that density is division of mass over volume. But what I want to talk about is a specific gravity. You know that a specific gravity is the gas density over the density of air if you are referring to a gas, and for the liquids the specific gravity is the liquid density over water density. There's an important question here: water density at what temperature? Or for the gas, air density at what temperature? And I should add here, I'm sorry, these are misplaced. This explanation is for the upper one and this one is for the lower one. Actually, for the liquid you should ask at what temperature. For the gas you should ask at what temperature and pressure. Do you know the answer for water, for example? Generally for water, water at, for example, 20 degrees C is taken as a reference. But for the gas or air, there are some different standards. I have written here some of the international standards in this regard, and you can see that there are different standard or base conditions for density or a specific gravity calculation. You can see, for example, that there are in the NIST, for example, you have a temperature of 20 and pressure of 1 atmosphere. But at the same time, there are also standards, for example, where the temperature reference is 60 degrees Fahrenheit, which is approximately 15.6 degrees C, and 1 atmosphere pressure. Actually, the pressure reference for all of them, as you can see, is 1 atmosphere, but the difference is about the temperature reference. So keep in mind when you are calculating the specific gravity of gases, this may make big differences in the calculation, and in some industries there are some discussion about that. Please keep in mind. A short note about pressure also. You know that pressure is a very important parameter. For pressure in fluid mechanics we have two reference points. The first reference point is the absolute zero. If you measure a pressure, for example this pressure referring to with reference to the absolute zero, then the pressure is named absolute pressure. But if you measure the pressure, the same pressure, in regards to the atmospheric pressure, please note local atmospheric pressure. With reference to the local atmospheric pressure, then it is named gauge pressure. So if you have a gauge like this one which reads 0 when it is open to the atmosphere, then it's a gauge pressure, okay, or it measures gauge pressure because it shows the atmospheric pressure as 0. If you move this gauge from, for example, a city in an altitude, high altitude, to a city near sea, do you think that the pointer will move, for example, to the left or right? What do you think? Suppose that this pressure gauge, which is a gauge pressure measurement device, is moved from, for example, sea level to a higher level, for example, above a mountain. What do you think? Do the pointer change its location? No, because it measures the gauge pressure, and gauge pressure is everywhere is 0, either at the sea level or above a mountain. But what about this? This is an absolute pressure gauge, and you can see that when it is open to the atmosphere, it reads a value. What is this? This is the atmospheric pressure, which is the gauge is reading, and the atmospheric pressure then will change if you move this gauge, for example, from the sea level to another higher level. Okay, Just I wanted to remember this because we may encounter these definitions later. The next section is the governing equation for pressure. You may remember, I'm not going into the detail because all these topics you read in the bachelor course. I'm just reviewing the points. Regarding pressure at a point, you know that pressure is a scalar quantity, and you can demonstrate, you can refer to the basic fluid mechanics books, that pressure at a point in a fluid is the same in all directions. So if you decrease the size of this element to an infinitesimal one where delta x, delta z are reaching to 0, then at the limit you will get this result as P1 equal P2 equal P3, and so all of them can be shown by a simple or unique P. So pressure at a point in a fluid is the same in all directions. The next topic in pressure is the governing equations for the static fluid. If you have a static fluid or a stationary fluid and take an element like this and show the free body diagram and write the Newton's second law, as there is no acceleration, then sigma f will be 0, and if you write, for example, the equation as you can see here, you'll reach to this conclusion. In the limit as delta z goes to 0, delta z is this, then you'll reach to this conclusion as dp over dz is minus rho g. So if you integrate this equation between 2 points, and you'll reach to the conclusion shown here. And for constant density and constant gravitational acceleration, you can take rho and g outside the integral, and you reach to the conclusion, to the simple conclusion shown here. Here I've shown a tank, for example, where the pressure variation is shown. As you can see, at the surface the pressure is 0, or atmospheric pressure if you take it absolute, and the pressure is, as you can see, is varying linearly up to the bottom of the tank. Please, so linear variation of pressure with depth you have, but there is an important point again here to remember about the assumption. Do you remember them? What were the assumption if you want to have a linear variation? Can you remember? Yes, here you can see the assumption for constant density, where you can take rho out of the integral, and constant gravitational acceleration. Generally gravitational acceleration may be taken as constant. By taking rho as constant should be done with precaution, because in some cases rho actually may not be constant, especially for gases where rho is changing with pressure and temperature both. Please keep in mind. You may have an example in the final exam about this. And as you know, this is the Pascal law, okay, the well-known Pascal law. What are the application? And one of the application is, as you can see here, for example, the variation of atmospheric pressure with height from the sea level. As you know, increasing the by going up, the pressure will be decreased. Actually, why? Because you have low mass of atmosphere above your head. Another interesting application is the hydrostatic paradox, as they say. For example, this is the question you may encounter before. You have 3 tanks like this one, the middle one, and the right one. The question is generally, which one has the biggest pressure at the bottom surface? Do you know the answer? For which one the pressure at the surface is higher? H is the same for all, but here the mass of liquid is less, here it is more, here it's something a bit in between. Yes, the pressure is the same at the bottom of the plates. Okay, this is named as the hydrostatic paradox. Another application is communicating pipe. You know that when two pipes are the pipes are connected like this, the surface of the liquid at both legs, actually these are named legs, is the same. Another application is the U-tube manometer. By this method, you know that by use of Pascal law, you can calculate the pressure at a point by connecting it to the U-tube manometer, filling it with a liquid, and then you can measure the height difference between the two sides, and by knowing the height difference, simply you can calculate the pressure difference by the Pascal law. Another application is you can see here actually, and it's very well known. I think I'm sure that you have seen it before, so let's pass it. Okay, another application of the Pascal law is the hydrostatic forces on surfaces. You may remember from fluid mechanics again that we have generally two types of surfaces. The first is the plane surface, like the gate you can see here. This is a slice gate, and if the gate is a plane surface, either like the one you can see here as vertically positioned, or it may be sloped like the one shown here. Actually, the vertical is also a special case of a sloped one. You may refer also again to the basic fluid mechanics books, but just some important points here is that the pressure, the resultant pressure, will be applied at a point which is named center of pressure. Center of pressure is different from the centroid of the body. In the special case when the plate is horizontal or the surface is horizontal, then C and CP, you can think about them yourself. But when the surface is sloped, you can see that always center of pressure is below the centroid. Okay, center of pressure is always below the centroid. The distance between, please note that centroid is a property of the surface, but center of pressure is not a property of the surface. So I mean that it's not a fixed point. For example, if you go deeper below the surface, below the free surface, then the distance between centroid and center of pressure will be decreased. But please note that C is fixed. Center of pressure is going towards C when the depth of submergence is increased. So for the sloped plane surface, where vertical is also a special case of a sloped, the center of pressure is at a point below the centroid. If the surface is curved like the one you can see here, then there are two force components. Actually, there is one force, resultant force, where there are two components of the resultant force. For the sake of simplicity, we do it like this and calculate these separately and then combine them together to find the resultant force. Okay, you can see that the force on a curved surface can be divided into a horizontal one and a vertical one. The horizontal force is actually can be calculated as the force on the vertical projection of the curved surface, as you can see here. CB or BC is the vertical projection of this surface, and FH is the force acting on the vertical projection. Calculating the force on the vertical projection is simple and can be done like the one shown here in the previous slide, and the center of pressure is also known. But what about the vertical force? The vertical force is can be calculated as the volume of the liquid, either actual or apparent one, because in some cases you may have liquid here, then the value, the absolute value of the force will be the same, just the sign will be different. The sign will be toward top of the liquid. So for the case shown here, FV is the weight of the fluid above the curved surface up to the free surface. Don't forget, up to the free surface. So you should calculate the weight of liquid in this space. Okay, then you can calculate the resultant force. Another application in fluid statics is the stability of the floating bodies. Floating bodies like the balloon you can see here. For the floating bodies like the one here, which are actually submerged in the air, the condition for the stability is that you can see here at the left. For stability of the floating bodies, the center of gravity should be below the center of buoyancy. You know that for any volume of body which is submerged in a fluid, there is a center of buoyancy, which is the center of volume actually of that body. So if the buoyancy center or center of buoyancy is above the center of gravity, then this will be stable. If it's in reverse and the center of gravity is above the center of buoyancy, then this will be unstable. And in the special case where both are at the same point, it is named as neutrally stable. So this is our interesting case actually, because this we like actually to happen. For this case, center of gravity should be below the center of buoyancy. But what about the floating bodies? I am really sorry because the topic here should be immersed bodies, and the topic here should be floating body. I'm sorry for that. So here we have a stability of immersed or submerged bodies. Here we should have the stability of floating bodies. Okay, as this is a recorded video, so you can, I think, correct it yourself when you listen to it. So for the floating bodies, the situation is somewhat more complex actually. The case where center of gravity is below the center of buoyancy is stable, no doubt, like the previous one. But there is a special case also where the center of buoyancy is below the center of gravity and still the ship or any floating body is stable. How it can happen? If you extend the direction of center of buoyancy like the one shown here, and draw a line in the center line, center of gravity, and find the intersection. If the intersection, which is called metacenter, is above the center of gravity, then this is stable. But if, like the one shown here, when you extend B, okay, and find the intersection of G line with this line, then the point of intersection, metacenter, which is below the center of gravity for this case, makes the body to be unstable, and this may happen as you can see here. This is an interesting topic also. The next application for the fluid static is rigid body motion. You may remember that in last week actually we have a discussion about the rigid body motion. If you remember, when a body of fluid moves at a constant acceleration, either in a horizontal road or even in a slope road, or a body of fluid like this one rotates about its own or any other axis, then this at the steady case, at the final steady case, can be taken as a rigid body, or the equations of fluid statics apply to both these courses. This is a linear rigid body motion, and this is a rotational rigid body motion. In both cases, the shear stress is zero, as there is no relative motion between the fluid particles. For example, here and here there is no relative motion between them. so the shear stress will be 0 everywhere, and the governing equation will be those that are used in fluid statics. If you write the equation for this case, the Newton's second law for an element, as it is shown here, you reach to the conclusion that gradient of P plus rho g k equal the acceleration term. This is in a vector form. If you write the component, then corresponding equivalence between the similar terms can be written, and you reach to the conclusion that if you have acceleration in a general case, suppose a general case where there are acceleration both in the even in the x direction, in the y direction, and also in the z direction. There is also a gravitational acceleration which is present everywhere. So in this case, we suppose that acceleration is in the minus z direction, and there are three acceleration: ax, ay, az. In this case, you can reach to the conclusion you will have three equations. Gradient of p in relation to x is minus rho ax, the same for y direction, and this is for the z direction. So there are some special cases. I repeated the equation in the previous slide again here for simple reference. For the special case where the fluid is at rest and there is no acceleration, ax, ay, and az will be 0, and you will have this equation, which is actually the equation you had before. Here you see that we changed rho to dy. Yes, because p is varying only in the z direction in this case. It's not varying with x or y, so you can write dp over dz, which is the Pascal law. Another special case is free fall of a fluid body. Free fall means that actually ax, ay are 0, and az is equal to g in the minus side, so it will be g minus g, which will be 0. So you reach to this equation, and as p is not varying either in the x, y, or z direction, then p will be constant. As I said before, another form of rigid body motion is the rotational rigid body motion. In this case, you should write the equation in the cylindrical coordinates, and if you read the vector form is the same actually, but if you write the components in the cylindrical coordinates, which is r, theta, and z, then you will reach to the conclusion that because there is only an acceleration like the one you can see here, and the acceleration of gravity, so you will have this equation. The equation then can be simplified to find the free surface equation by putting p equal to 0 at the free surface, because at the free surface p is the atmospheric pressure, which is 0. Integrating the equation and putting the boundary condition at the surface, you reach this conclusion, which shows the form of the free stream, which is a parabola. So for a rotating cylinder, the shape of the free surface will be a parabola like the one you can see here. Okay, I want to mention here as the last slide that please read some maths. For example, you should know about the operator in the next session. Next week, for example, you should know the definition of gradient carefully. You should know the definition of Laplacian. You should know the definition of divergence, and you should know the definition for the curl of a vector. These are very important. And you should know them very carefully. Okay, this is end of part 2, and I ask you to see this video again if there are some doubt in some parts, and ask me your question at the beginning of next session. Thank you and take care.